Phase equilibrium. What are the conditions for two different phases in contact to be at equilibrium? We have here an isolated system, which is partially filled with saturated vapor and partially with saturated liquid. The system is at equilibrium, so both the vapor and liquid are in equilibrium with each other. Let us first discuss the nomenclature that we will use to describe such a system. We will use the subscript F to denote the properties of the saturated liquid. F is chosen as a subscript because in German, Flüssigkeit means a liquid. Most of the original work on this subject was done in Germany by Clausius. G will denote the saturated vapor, which is gas, which is the same word in German. We will start to analyze the equilibrium of such a system with the state postulate. So for the liquid, the entropy, S sub F, is a function of the internal energy, U, the volume, V, and the mass, M, of the liquid. Similarly, for the vapor, the entropy S sub G is a function of UG, VG, and mg. Entropy is an extensive property, so S, which is the entropy of the combined system, is equal to SF plus Sg. Finally, the second law states that at equilibrium, the entropy is a maximum, so therefore ds is equal to 0 at equilibrium. We have an isolated system, so the total mass, volume, and energy are fixed. Therefore, U, which is the internal energy of the total system, which is equal to UF plus UG, is constant. Similarly, the volume, V, is equal to constant, and the mass is constant. Differentiating these three equations, we get that DUF is equal to minus DUG. dVF is equal to minus dVg, and dMF is equal to minus dMg. These three are known as the closure conditions. We can use the Gibbs equation to calculate the change in entropy. So Ts is equal to du upon T plus P upon T dV minus G upon T dm. Let's write the Gibbs equation for the liquid. So TSF is equal to DUF upon TF plus PF upon TF times DVF minus GF upon TF times DMF. The Gibbs equation for the vapor becomes TSG is equal to DUG upon TG plus PG upon TG times DVG minus GG upon TG times DMG. Now from our closure conditions, we know that DUG is equal to minus DUF, DVG is equal to minus DVF, and DMG is equal to minus DMF. Substituting that, for the vapor we can now write that DSG is equal to minus DUF upon TG minus PG upon TG times DVF plus GG upon TG times DMF. The equilibrium condition for an isolated system says that the change in entropy, ds, which is equal to dsF plus dsg, must equal 0. If we substitute the expressions for dsF and dsg that we just calculated from the Gibbs equation, ds is equal to 1 upon tf minus 1 upon tg times duf plus pf upon tf minus pg upon tg times dvf minus gf upon tf minus gg upon tg times dmf, and this must equal 0. Now, since we know that duf, dvf, and dmf can have arbitrary values and they are independent, all three of the quantities in brackets must equal 0. If we set those three equal to 0, then we say that at equilibrium, Tf is equal to Tg, Pf is equal to Pg, and Gf is equal to Gg. The first two conditions we are already familiar with. We know that the pressure and temperature are uniform in a system at equilibrium. The third condition is a new one. So we have that at equilibrium, Gf is equal to Gg. The specific Gibbs function is also known as the chemical potential. And what this condition tells us is that there is no exchange of mass between two phases whose chemical potentials are the same. What if the system is not at equilibrium? In that case, the entropy must increase so that Ts is greater than 0. Let us assume that we have uniform pressure and temperature everywhere in the system. In that case, Tf is equal to Tg and Pf is equal to Pg. However, we assume that the chemical potentials of the two phases are different and that Gf is greater than Gg. If we then write our equation for ds, this is greater than 0. However, if the temperature and the pressure are equal, then the first two terms go to 0. ds is then equal to minus 1 upon Tf times Gf minus Gg times Tmf, and this is greater than 0. If Gf is greater than Gg, then this term in brackets Gf minus Gg is greater than 0. For this inequality to be satisfied, Tmf must then be less than 0. The physical meaning of DMF less than 0 means that we are getting mass transfer from the phase F, which has the high chemical potential, and that mass is transferred to the phase G, which has the low chemical potential. Mass transfer takes place from the phase with higher chemical potential to the phase with lower chemical potential. This gives us insight into the physical meaning of the chemical potential. So temperature is a potential for the transfer of energy in the form of heat. Energy is transferred from the region of high temperature to the region of low temperature. Pressure is a potential for the transfer of energy in the form of work. So energy goes from the region of high pressure to the region of low pressure. Chemical potential is a potential for the transfer of energy along with mass. So mass is transferred from the region of high chemical potential to the region of low chemical potential. And internal energy is transferred along with the mass. Suppose we have a system like this, which is partially filled with liquid, but has a vacuum above it. If there's a vacuum, the chemical potential there is equal to 0. So the liquid, which has a higher chemical potential, will begin to evaporate. As it fills up the vacuum, the chemical potential of that will start to increase. And this will continue until Gg is equal to Gf, and we have a state of equilibrium. After that, the liquid will not evaporate anymore. On the other hand, if we leave liquid in an open container, then the chemical potential above it always remains 0 because there's nothing to stop the vapor from diffusing away. So in that case, the liquid level will keep dropping until it completely evaporates and all the liquid dries out. How do we evaluate the chemical potential? Let us start by writing the definition of the Gibbs energy. G is equal to H minus Ts. If we substitute in this the definition of H, we get G is equal to U plus PV minus Ts. Differentiating this, we get that dG is equal to du plus pdV plus vdP minus TdS minus S dt. All of these terms, dV, dP, dt, are easy to measure. du can be related also to the change in temperature. ds is something that we need to determine. We can do that using the Gibbs equation. So ds is equal to du by t plus p upon t dv minus g upon t dm. Let's substitute ds back into our equation for dg. If we do that, we get that dg is equal to du plus p dv plus v dp minus du minus p dv plus g dm minus s dt. Now, a number of these terms cancels out. So du cancels out, p dv cancels out. We get dg is equal to g dm plus v dp minus s dt. So this gives us the change in Gibbs energy, dg, is then equal to g dm plus v dp minus s dt. The first term is due to the change in mass of the system, dm. The second is due to the change in pressure, dp. The third is due to the change in temperature, dt. So the Gibbs energy can change because of changes in mass, pressure, or temperature of the system. The total Gibbs energy, G, is the product of the specific Gibbs energy, the lowercase g, times the mass of the system, m. So dg is equal to g dm plus m dg. If we equate this to the earlier equation that we had for dg, we get that g dm plus m dg is equal to g dm plus v dp minus s dt. G dm cancels out on both sides of that equation. We are left, therefore, with m dg is equal to v dp minus s dt. If we divide this equation by mass, we get that Tg is equal to V dP minus S dt. V over here is the specific volume and S is the specific entropy. This equation is known as the Gibbs-Duhem equation. And what it's telling us is that the chemical potential varies with changes in temperature and pressure. We will use this equation, therefore, to calculate the changes in chemical potential. To summarize, there is no exchange of mass between two phases whose chemical potentials are the same. Mass transfer takes place from the phase with a higher chemical potential to the phase with lower chemical potential. Chemical potential varies with temperature and pressure, and we can calculate changes in chemical potential using the Gibbs-Duhem equation, that Tg is equal to V dP minus S dt.